Most transformers that are purchased or given to you as an electrician to install already have the terminals tagged. Those with the prefix H are the higher of the two voltages, if there's two voltages with it, and those with the prefix H are the lower of the two voltage. However, there are times when you're handed a transformer that are missing the tags, look, they fell off the back of a truck. So how do you determine which is which? So how do you determine which are the terminals? And one way of doing it is by an ohmmeter. If you put an ohmmeter or you use an ohmmeter to test for continuity, there will be an actual reading, an ohmic value between two terminals that are connected to the same winding. Now what you'll find is that the ohmic reading or the ohm value will be less for power transformers and it'd be higher for actually instrument or low power transformers. Now if you connect your ohm meter between two different windings, what you'll find is you'll get the open loop signal, which means that there is infinite resistance, or there should be infinite resistance between these two terminals. Now, one way of determining which is the high voltage side is the high voltage side will have a greater resistance than the low voltage side, usually because of the many turns of very light wire, whereas the low voltage side will be expecting more current than the high voltage side and will have a lower voltage and its resistance will be lower. First test we'll talk about is the Megger insulation test. Okay, what it does is it provides a high voltage to the conductors, testing to see if the insulation actually breaks down under stress. It comes in various voltage levels: 50, 100, 250, 500, or 1,000, and some can go as high as 5,000. The reading is actually in ohms, but instead of just being in ohms, it's kiloohms, megohms, or gigohms, because the value should be very, very high. You should have very high resistance values between any conductor and ground or the chassis. This should be performed first on any major piece of electrical equipment. I say major because you wouldn't test every light switch and every light socket or light bulb socket that you put in. But if the insulation is bad, all other tests are meaningless. This piece of equipment cannot be used. Let's look at the voltage that electrical equipment is subject to. Electrical equipment is usually rated an RMS voltage, which is less than peak voltage. Peak voltage you can obtain by taking the RMS voltage and multiply it by 1.414, which is the reciprocal 1 over 0.707. Okay, electrical equipment actually under normal operations sees this voltage, which is much higher than RMS. Since each electrical piece of equipment actually is subject to this peak voltage, if we look at a piece of equipment rated for 120 volts AC, the peak voltage is actually very close to 170 volts. To test the insulation with less than that voltage would be inconclusive or undetermined. You're not really testing the insulation. You have to stress it has to be over the standard voltage. So rule of thumb, to make it easier, minimum test voltage should be at least 1.5 times the volts RMS. Okay, well, which in this case is actually 180 volts, which is higher than V peak. But the Megger, it doesn't have 180 volt setting. It has a 250 volt setting. So we'd use the 250 volt setting on the Megger to test this piece of equipment. So what kind of reading should you get? The insulation resistance to chassis or ground should be approximately 1 megohm for each 1,000 volts of operating voltage, with a minimum value of 1 megohm. It should never, ever be below 1 megohm. If it is, then the piece of equipment is no good. Now, let's say, for example, I was to take a 2400 volt motor or transformer. What would be the minimum resistance would be 2.4 megohm. However, in practice, if you have a piece of equipment that is new or the insulation is good, you really should have something much higher than this. My recommendation would be 10 megohms minimum for a brand new piece of equipment. So where and how do you test? First, it is always imperative to make sure you do have a good connection to any of the terminal points or to the chassis of the transformer. Once you've established that, what you do is you make a connection to the chassis and one to any one of the terminals and take the test from there. It is recommended that you test every terminal to make sure that there is no weak insulation between those windings and the chassis of the transformer. You must test everything in a transformer, and this, what we're showing in this presentation is actually very simplistic. But what you do test is between primary to the chassis or ground, from secondary to the chassis or ground, and between the two windings, which would be from primary to secondary. This way you can ensure that the insulation to the chassis, between the conductors in the chassis, or between the conductors of opposing windings is in fact good. So let's look at what a transformer ratio is. Transformer ratio is really, if there's an increase in the primary voltage, there will be a corresponding increase in the secondary voltage with respect to the transformer ratio itself. So if it's a 2 to 1, for every 2 volts on the primary, you have 1 volt on the secondary. If I have 20 volts on the primary, what I would have is 10 volts on the secondary. Now, if you're going to test for transformer ratio to see if it's okay, what is required is a variable voltage power supply. You seek out the high voltage connection. Well, how do you do that? That would be the winding with the highest ohmic value. And what you do is put the variable voltage supply across it and slowly turn up or increase the amount of voltage applied to the transformer and measure the voltage on the secondary. Okay, so if we look at transformer ratio with respect to current, if a transformer has a load, in other words, in the secondary winding or connected to the secondary winding is a path for current to flow, an increase in the primary voltage will cause an increase in the secondary current. You have to remember that the load is what determines how much current is going to flow or how much load is applied to the transformer. The ratio of the secondary current is the inverse of the transformer ratio that we had for voltage. Theoretically, if I have no load on the secondary of a transformer, then there should be no current flowing in the primary. However, this isn't really the way practical transformers work. If I have the rated voltage applied to the primary, very small currents will flow in the primary. This is usual, and it's there to compensate for losses in the transformer and also to maintain the magnetic field. If the no load primary current, however, is greater than 3% of full load current, what really should be suspected or looked for is a turn-to-turn short in either the primary or the secondary windings. This is a fault. This may not show up in the Megger test, but does show up when you do this no load voltage test. Also, in practical transformers, under no load or full load conditions, there can be large inrush currents can occur. They actually can be large enough to trip or blow the overcurrent protection. This can be still a good transformer. This doesn't mean that the transformer is bad. This magnetizing current is really totally inductive. It is just that current that occurs to try to build up and charge up that magnetic field once the transformer is energized or put online. Okay, so let's have another look at these random currents. Small currents can flow in the primary with no load on the secondary, usually in the order of a few milliamps. However, keep in mind that the larger the transformer, the larger these excitation currents can be. Keep in mind too that if it's greater than 3%, you probably have a turn-to-turn short in the transformer. These large inrush magnetizing current large current that flows into the primary at the initial energizing of the transformer, and they could actually cause the overcurrent protection to open. Keep in mind though that this can be intermittent. It all depends on when you energize the transformer. If you energize the transformer at the peak of the AC cycle, magnetizing current is going to be greater, and if you energize it at the zero of the AC cycle, the magnetizing current will be less. Next is a polarity test. In some cases, it is really essential to know the polarity of the transformer. Keep in mind that transformers don't have negative or positive, they're AC. What it does is it determines that what terminals on the transformer are at the same polarity at the same instant of time. So let's look at this transformer. It's a 600 to 120, 240 volt. The transformer ratio is 1 to 2.5. That is 600 to the 240 volt. If the transformer ratio isn't known, it can be found by applying a small voltage to one winding and measure the voltage at the other. You should always apply your test voltage to the high voltage side. To begin with, to do the polarity test, we connect one terminal of the primary to one terminal of the secondary. That puts the two windings actually in series, and we assign a polarity dot to one of the terminals on the primary. You should always apply your test voltage to the high voltage side. Remember, that can be determined by which winding has the highest ohmic value. Okay, so apply an AC voltage to the winding with the polarity dot. However, this voltage does not have to be rated voltage. It's safer to use a voltage that is lower than rated voltage. Okay, let's look at it as an example. We should be testing, of course, from the high side, the high voltage side, which we can tell by our ohmic reading, higher ohmic reading for higher voltage. What we would do is apply a 24 volt voltage to the primary side, read by voltmeter V1. Voltmeter V2 should actually read 9.6 volts, or somewhere close to that because of the transformer ratio. The key here is reading voltmeter 3, which will, if it's the sum of the two voltages, in this case 33.6 volts, then the connection here is additive, and you can assign a polarity dot. Once you assign the polarity dot, and then you can actually assign terminal designations, H1 being where the high voltage polarity dot is, and X1 being where the low voltage polarity dot is, and then the other terminals. Let's look at another example. We apply the same 24 volts AC, and we actually read the same 9.6 volts at the secondary. But if we read voltmeter V3, what we see is it's actually the difference between the two voltage, 14.4 volts. This means that they're being connected in series. They're of opposite polarity connection, and you assign your second polarity dot and then assign terminal designations or terminal tags as seen here in this illustration. Okay, next let's look at the capacity of supplies, and transformer actually is a type of supply. Each supply has a capacity, that is to do that how much power or voltamps that it can actually put out. Looking at the illustrations here, we have two batteries. Obviously the one's a 9-volt battery, but regardless of the voltage, you can't expect the same amount of power out of the 9-volt battery as you can the car battery. Okay, as with all supplies have losses. There's internal losses in the supply. Any unregulated supply output voltage will decrease under load. That is to say that as soon as I start drawing current from that supply, its terminal voltage will actually drop. Some of these losses can't be measured directly. We can't directly measure hysteresis losses or core losses. We could measure copper losses if we know the resistance and the current that's flowing in the transformer. Okay, but the effects of these losses can be measured, and they will determine the characteristics of the transformer as in percent impedance. Okay, so the next test we're going to do is an impedance test. Impedance of a transformer is expressed in percent impedance. And you'll see it on the nameplate of the transformer, percent Z. And it can actually be used to determine short circuit currents and full load voltage. Okay, so the impedance test is done by, first of all, what you have to do is determine the secondary full load current, FLA. You connect a variable voltage supply to the primary and connect a voltmeter across that to determine the voltage which you're applying. You put an ammeter across the secondary or short the secondary. An ammeter really is a short. It has very little resistance to the flow of current. Or put in a short and use a clamp on ammeter. This isn't recommended to do across any active transformer applying full primary current or full primary voltage. This will cause an accident, a real problem. So you increase the primary voltage until you get full load current flowing in the secondary. Record the primary voltage, that is actually what's called the test voltage, and you divide the test voltage by the rated primary voltage, and that will give you your impedance, percent impedance. Okay, with this value of percent impedance, it's possible to calculate short circuit currents of the transformer or full load voltage of the transformer. Short circuit current, remember short circuit current is the current on the secondary of the transformer. That's where the load is. It's on the secondary of the transformer. Short circuit current is equal to the full load amperage divided by that number we've got by determining percent impedance. The full load voltage is equal to the no load voltage of the secondary minus the product of that no load voltage multiplied by the percent impedance, and that will give us voltage on the secondary under full load. Next, what we're going to do is a full load test. A full load test is similar to the impedance test. However, what we're doing here is we're going to make the same connections. We short out the secondary. We apply a variable voltage supply to the primary. However, this is done over a longer period of time. Okay, so first of all, what we need to do is calculate the full load current. That is to determine the full load current on the secondary of the transformer. Then what we do is short the secondary of the transformer. Now you have to be very careful not just to apply rated voltage to the primary. What you'll end up doing is vaporizing the conductor you put on as a short, and you can cause yourself great injury in doing so. So you have to be very careful doing these types of tests. You increase the supply on the primary until that calculated full load current is flowing in the secondary. Once you have the conditions set, allow the transformer to continue with full load current for a minimum of 30 minutes. Now, a good hour is actually recommended, but 30 minutes, what you'll be doing is passing full load current. The transformer's under maximum stress. If the full load current is not possible because you have limitations of the supply, your variable voltage power supply, you must at least test it with a minimum of 80% of full load current in order for this test to do any good. The transformer should get warm under this type of load, if not hot. If it remains under this full load current going for at least 30 minutes to an hour, the laws of probability really state that it will last for quite a long time under normal conditions. We don't normally expect to keep a transformer under full load conditions on any continuous period of time. Normally they're rated to be run at 80% load or less. The advantages of doing this is that the amount of energy we're using is much less than normally would be involved if we put a standard load across the transformer, the secondary of the transformer, and use rated voltages to the primary. This makes this type of test actually safer. Okay, here we have a nameplate of a transformer. It's a three-phase delta to Y, 208 to 208, 120. The percent Z in this case that will be on any nameplate of a transformer is actually expressed as a percent of 100. So you would take the percent Z we would get from our test, multiply it by 100, and that's what would appear on the nameplate.